everybody who is in distant learning. We have finished discussion of the laws of classical mechanics, and today we will go to a next topic, which is ideal gases. As far as classical mechanics is concerned, you remember we learned basic formulas of kinematics and Newton's laws of classical mechanics, and a law of conservation of momentum, and the law of conservation of mechanical energy, and rotational motion. These laws are very important. They are the basic part of classical mechanics, but certainly there are many other interesting and important questions in classical mechanics, which we will consider next semester. And so the next semester we will actually start from the same laws of physics, the Newton's laws and conservation laws, but we will use calculus and we will solve much more complicated problems. But today we will discuss a new topic. I told you, an ideal gas. To understand the properties of ideal gas, we must first define what is an ideal gas. An ideal gas consists of molecules which do not interact with each other. The molecules may collide with each other and certainly collide with the walls of the container in which the gas is contained, but the interaction between molecules is negligible. That is the definition of ideal gas. Certainly not all gases are ideal. There are many real gases, and actually any gas becomes real gas with somewhat different laws if you increase the density of this gas, or increase the pressure, or decrease the temperature. So the laws of ideal gases apply only to a limited range of pressures and limited range of temperatures. Anyway, these laws are very important. As we mentioned molecules, it's important to understand that people started thinking about atoms actually very long ago, about 25 centuries ago. In the ancient Greece, some philosophers understood that atoms must exist, and they defined atoms as the smallest indivisible part of matter. Actually, it's possible to understand from a very general view that atoms must exist. For example, if you take a small amount of any matter like water, if you take 1 gram of water, it will possess all properties of water. If you take much smaller part of it, like 1 milligram, 1,000 times smaller, it will still possess all properties of water. If you take still smaller part, 1 microgram, it will still possess some properties of water. And there is a natural question: is it possible to divide matter infinitely with retaining all the properties of this matter? It seems to be obvious that it's not possible. On some step of division, you will come to such a tiny particle, such a tiny portion of matter, that its properties will become different. from the properties of macroscopic amount of substance. It would be absolutely improbable if matter could be divisible infinitely. If whatever small part of matter you take, it will possess the same properties. It's impossible. From merely philosophical point of view, something should change. And so there should be the smallest part of matter, the smallest particle, which still possesses all the qualities of matter, like qualities of water. But if you divide this smallest part into even smaller parts, then the properties of matter will be changed, drastically changed. Nothing will remain from the original chemical properties. If you divide the molecule of water into parts, the parts will possess absolutely different qualities, different chemical qualities, and different physical qualities. If you divide the molecule of water into parts, you will obtain hydrogen and oxygen. Under normal conditions, these are gases, but water is liquid. So even the physical properties are changed if you divide the molecule into smaller parts. So the existence of atoms and molecules seems to be obvious and seems to be necessary from merely philosophical point of view. Now we know a lot of an abundance of proof that atoms do exist. First of all, we can see atoms. We can see them using electron microscope or using scanning tunneling microscope or STM or using some other methods. It's possible to see atoms. It's possible to measure the dimension or diameter of atoms. It's possible to measure the mass of atoms. So today's physics knows a lot about atoms, and atomic concept of structure of matter is the basic, is the fundamental concept of nature, which is necessary to understand the properties of gases, properties of liquids and solids. About 200 years ago, some people understood that atoms do exist, and they had more experimental data, more than ancient philosophers. And these experimental data were, first of all, diffusion. Diffusion of one substance when one substance penetrates into another substance. How can a diffusion take place if not by motion of small particles of matter? Another thing is Brownian motion, a motion of very small parts of matter, but still visible, small but still visible in an optical microscope. Such small particles as flower pollen. A flower pollen observed in microscope, in an optical microscope, exhibits random motion, chaotic motion. Each small particle of pollen chaotically moves about to and fro in different directions. And this is certainly a part of the Brownian motion. What was discovered by Brown and is called Brownian motion is actually a part of diffusion. Due to such random jumps, diffusion of particle, the process of diffusion is realized. So what do we know about atoms today? As all the parameters, many parameters have been measured, accurately measured, we can say that the dimension of atoms, the diameter of atoms, is approximately 1 angstrom. angstrom is 10 to the minus 4 power of micron, and angstrom is also 10 to the 10th power of meter, or correspondingly 10 to minus 8th power of centimeter. So it's very small distance, and that is approximately the dimension, the diameter of atoms. If we know the diameter of atoms, it's easy to calculate the mass of an atom. Well, for example, take some substance which is well known to you, like water. We will calculate approximately, we will assess the mass of a water molecule. If the diameter of molecule is like this, approximately by the order of magnitude, then the volume occupied by one molecule is about 1 angstrom cube, by the order of magnitude. And if we take the volume of 1 liter, then the massive volume of 1 liter of water will be 1 kilogram. So what may be the mass of this small volume of the same substance? We have simple proportion. This mass is unknown, the mass of one molecule. And according to the simple proportion, we may write that small mass, mass of molecule, or mass of atom, over 1 angstrom in cube is like 1 is related to 1 kilogram to 1 liter. 1 kilogram and 1 liter is 10 to the minus 3 meter cubed. So from this proportion, from this simple reasoning, we may derive by the order of magnitude the mass of an atom or mass of a molecule, which will be 1 kilogram times 1 angstrom cube divided by 10 to the minus 3 meter cube. Okay, what do we have here? 1 angstrom is 10 to the minus 10. If we take the cube, we will obtain 10 to the minus 30. (10 to the minus 30 meter cubics, and that is meter cube, cubical meter, and that is 10 to the minus 3 cubical meter, and that is 1 kilogram. So we obtain something like 10 to the minus 27 kilograms. That is, by the order of magnitude, the mass of a molecule, or typical atom. All atoms are practically the same mass. The mass may be 10 times less or 10 times more, but approximately by the order of magnitude, the masses of atoms and molecules, not very large molecules, but small molecules, which contain 2 or 3 or 4 atoms. Well, all these molecules will have the mass approximately in this region, in this range of magnitudes. So if we know that molecules are very small in dimension and very small in mass, then we can derive some properties of real substance, of real bodies. Actually, a lot of properties can be derived, like the density, and if we take into account some other properties of atoms, we can predict many properties of real matter. But today, now I will consider the properties of real gas, and we will derive some interesting things about the behavior of an ideal gas. So suppose we have a gas in a cylinder which is covered by a piston, and the piston can move in this cylinder freely up and down, changing the volume under the piston. So if we put some load here, some massive load, let it be capital M, the mass of this body capital M, then this load will push the gas downward with the force mg, and the gas will be compressed, and then it will be, the position of the piston will be balanced by the pressure of the gas. And if this area of the cylinder base is S, then the pressure of the gas will exert some force on the cylinder, and this force of pressure from the gas will keep the piston on its place, on some fixed position, so that the pressure, so that the total force acting from the gas will be equal to mg and oppositely directed. And the pressure itself is the force defined, pressure is defined as the force acting on a unit area. That is the force by, that is what we mean under pressure by definition. Pressure is a force acting on a unit area. That is, in this international system, that is a Newton over meter squared. This unit, 1 Newton over meter squared, is called Pascal. So the gas molecules here in this volume move chaotically in all directions, and there is a huge number of molecules, billions and billions of molecules, and all of them move quickly in different directions. And if you heat the gas, if you increase the temperature of the gas, then its pressure will be increased and the piston will go up. Because of larger pressure of the gas, the piston will go up. So we know from simple experiments that the pressure of the gas somehow depends on the temperature of the gas. And also, if we compress the gas and decrease the volume, then the pressure will increase. So the pressure depends on both temperature and volume. That is obvious. There must be some analytical connection between pressure, volume, and temperature. And we will derive this connection now. And the derivation will be based on molecular kinetic understanding of what's going on inside an ideal gas. I told you that ideal gas is characterized by the fact that there is no interaction between molecules. Sometimes there is an interaction when molecules are close together. There is an interaction. If molecules form a liquid rather than gas, then they interact strongly. And if the molecules form a solid state, then interaction is even more efficient. So in order to draw a line, in order to distinguish between solid state bodies and liquid bodies and gaseous bodies, it's important to understand what parameter defines the state of the body, whether it is solid or liquid or gaseous. So if molecules interact, then there is such a concept as such a quantity as a potential energy of interaction. In any interaction, there is some characteristic potential energy. Also, if molecules move, then there is a kinetic energy in molecules. So if kinetic energy of molecules, which depends on temperature, kinetic energy, which is a function of temperature, is much greater than the potential energy of interaction between molecules, then we have gas. So this is gas. If potential energy, if the kinetic energy is approximately the same order of magnitude as the energy of interaction, potential energy of interaction, then we have liquid. And if the kinetic energy, which is a function of temperature, is less than the potential energy of interaction, then this is solid state. So everything depends on the relationship between the kinetic energy of molecules and the potential energy of interaction between them. In all these cases, we obtain different states of matter. So in the gas, kinetic energy of molecules is much larger than the potential energy of interaction. So the interaction can be neglected. And we say that the molecules in an ideal gas don't interact. Yeah, surely they do, but we neglect this interaction because it's very small. The potential energy of interaction is very small as compared to the kinetic energy of molecules. So in order to derive some equations related to an ideal gas, let's consider a single molecule here, a single molecule. A single molecule moves chaotically in different directions. I will draw a different sketch, somewhat larger. So we consider a single molecule. It moves in different directions, but whatever direction it takes, there is a component of velocity directed along the x-axis. In our case, horizontal component, which is perpendicular to the walls of this cylinder, of this container. So there is some horizontal component at whatever speed, whatever velocity is of this molecule, whatever velocity it has, there is always some horizontal component. It may be zero, but in general case, it's non-zero. And the molecule has some mass. It's very small, but anyway, there is a mass. So the molecule has some momentum, which is mvx. And when the molecule strikes the wall, when it hits the wall, it's reflected from the wall, and we assume that the wall is an ideal mirror. It acts on the molecule like an ideal mirror. So the molecule reflecting from the wall will change its horizontal component of velocity from Vx to minus Vx. It will be reflected from the wall. How often this molecule will hit the wall? It will take the molecule some time to travel along the container from one wall to another and then again to this first wall. When the molecule travels from the first wall to the second one and then back to the first wall, it will cover the distance 2L. The distance covered will be 2L. And if it travels with an average velocity Vx, so it will take time 2L over Vx. That will be the time interval between the two consecutive hits of the same molecule against this wall. So every time interval t, the molecule will hit the wall. And the momentum of the molecule will change from mv to minus mvx, because the velocity will change from vx to minus vx. So the total change of momentum will be 2 mvx. That is the total change of momentum, the magnitude of momentum will change by this value each time the molecule collides with the wall. And this happens during time interval t. Well, it's better to say that this is delta t. That was our original notation. And so according to the formula for the change of momentum, the change of momentum must be equal to a force times delta t. And we know what is delta t. It is 2L over Vx. So from this equation, we know the change of momentum each time the molecule collides with a wall, and we know how this change of momentum is related to the force, the mean force which the molecule exerts on the wall. It strikes the wall many times, probably many times a second. And on average, this hitting the wall will push the wall slightly rightwards. And that means that some force, average force, is acting on this wall from this single molecule which is flying here. So we can calculate, we can assess this force from this equation. It will be 2 mvx squared over divided by 2L. 2 and 2 will cancel, and what we have is mvx squared over L. That is the force acting on the wall from a single molecule. If there are many molecules, like billions and billions of molecules here, and each single molecule exerts this force F, and the total number of molecules is n, then the total force exerted by all the molecules will be n times larger. We will have to multiply this by n. That will be the total force exerted by all the molecules on the side wall. But actually we don't need force, we need pressure. And in order to obtain pressure, we recall that pressure is a force acting on an unit area. So we have to divide the force by some area of this side wall. So after dividing this formula by area, we obtain the total force, which is, let me denote it by such letter F. The total force divided by area of the side wall will be equal to mvx squared number of molecules divided by ls. And if we choose a container like a cubical form, then the area of this face of container multiplied by L will give its volume. So what we have here is the volume of the container. It's obvious that the formulas obtained will apply to different containers, different forms, but it's easy to derive the formula for a rectangular cubic form container. So what we have here, this will be a pressure of the gas, and from here we obtain that pressure times volume is mvx squared number of molecules. Now, as far as the Vx squared is concerned, we must understand that the choice of axis x in this direction was arbitrary, and we have just chosen it arbitrarily. We could have chosen any other axis for our derivation. We could have chosen axis y, or we could have chosen axis z. So in any direction, the molecule, the average or the mean square speed of molecules will be the same in any direction. Whether I take the x direction, or whether I take the y direction, or whether I take the z direction, all the directions are similar. They don't differ from each other. And in a gas, all directions are identical. And the velocities of molecules are chaotically directed in different directions along different axes. So all these velocities are the same. Certainly, different molecules may have different components, Vx, which may differ from Vy. But what we are talking here in this equation is the mean square component. That is the mean square, to underline that this is not the velocity of a given molecule, but some average velocity. I will put such a line above this symbol to indicate that this is a mean square velocity, not the velocity of a single molecule. This is the mean square velocity. All of them are the same. And also for each molecule, if we consider the velocity squared, from Pythagorean theorem, we have that this velocity squared is Vx squared plus Vy squared plus Vz squared. And this is true for mean squared velocities. And as all these terms are equal to one another, as we have established, then actually Vy equals Vx squared, and Vz also equals Vx squared. So here we have 3 Vx squared mean square velocity of x component. So the mean square velocity component along the x-axis will be the mean square velocity v over 3. We divide by 3 in order to obtain this quantity. So returning to our original formula, I may substitute v square velocity for vx square velocity, and that will give me m v square velocity average over 3 and the number of molecules. we have here mv squared over 3. And you remember that the kinetic energy of a body is mv squared over 2, divided by 2. So this term is proportional to a kinetic energy. Now, as we have mean velocity, mean square velocity, then we must talk about mean kinetic energy of all molecules in the gas. Mean kinetic energy of all molecules in the gas, by definition, is proportional to absolute temperature. And there is a coefficient of proportionality. So this is absolute temperature of the gas with some coefficient which depends on the choice of units of measurement. So we can put it here like K, some constant, N, another constant, and T. This constant is called the Boltzmann constant. The Boltzmann constant, the constant of proportionality between the mean energy, actually between mv squared mean over 3 and the temperature. So what we get here, if we go to mean kinetic energy, let us denote the mean kinetic energy by epsilon. It must be m v squared average over 2. So in terms of mean kinetic energy, Boltzmann constant and absolute temperature will equal to 2 divided by 3 epsilon. So that the absolute temperature is proportional to the mean kinetic energy, but the coefficient of proportionality is 2 over 3. If you substitute here mv squared over 2, 2 will cancel, and we will obtain mv squared over 3. That's the relationship between the mean kinetic energy of molecules in the gas and the temperature of the gas. But what we obtained here is very important. What we obtained here, the formula is so important that I will write it down again and discuss the consequences of this formula. So we obtain that pressure P times volume V, gas pressure times the volume of container in which the gas is kept, equals the number of molecules, Boltzmann constant K, the absolute temperature. This is a very important formula which gives you a lot of consequences, important consequences. First of all, if temperature is constant, if we keep the gas temperature constant, we sustain it constant artificially, but at the same time we change pressure and volume, then we obtain that pressure times volume is constant. And it means that pressure the graph of pressure versus volume will be something like that. If the gas has initial pressure and initial volume, then this point on this diagram will represent the state of the gas. If we increase the volume, then the pressure must decrease. So that such will be the diagram showing the behavior of the gas at constant temperature, the pressure will be inversely proportional to the gas volume, the gas pressure and the gas volume. So the gas pressure is inversely proportional to the gas volume. This is a Boyle's law. Another situation is if we keep the volume constant, the gas volume is constant, so that we fix the position of this piston. We don't allow the piston to move. We fix the volume of the gas. And for example, we may change temperature, we may heat the gas. And look how pressure will change. If volume is constant here, then pressure will be simply directly proportional to temperature. Pressure will be directly proportional to temperature. And the graph showing the dependence of pressure versus temperature will be this. It will be directly proportional to temperature. Also, if pressure is kept constant, that is, we allow the piston to go wherever it wants, and we keep a constant load here, so that the piston will press the gas with constant force. And as the area of cross-section of the cylinder is constant, the pressure of the gas will be constant. If we just allow the piston to move up and down with constant load, then the pressure will be constant. And in this case, if pressure is kept constant in our experiment, then what this formula gives, that the volume will be proportional to absolute temperature. The volume of gas directly proportional to temperature. And the graph showing the dependence of volume versus temperature will be like this, again directly proportional. Historically, experiments in which the volume of the gas was changed if the temperature is changed under constant pressure. Historically, such experiments were used to define the temperature scale. That is, if we choose temperature of water freezing, when water freezes, this temperature of freezing water is accepted to be 0. And then we choose another temperature when water boils. That will be 100 degrees. 100 degrees. By convention, we could have divided this interval of temperatures into some other number of degrees, but by convention, this range of temperatures was divided into 100 degrees. And then we may experimentally change temperature, and at each temperature measure the volume of gas. At each temperature we can measure the volume. And then these points, which can be obtained here, will may be approximated by a straight line which will go to 0 volume at some large negative temperatures. And experimental measurements show that this temperature is minus 273 degrees. Such is the Celsius scale of temperatures. The Celsius scale is defined in this way. First we find the temperature at which water evaporates. That is 100 degrees under normal pressure, under the pressure of 1 atmosphere. And then we find the temperature when water freezes into ice. And the range of temperatures will be divided by 100 degrees. And if we conduct this experiment and measure these points here, experimental points, and then approximate this line with a straight line, then the straight line will go down at minus 273 degrees, which is an experimental data, experimental fact, which is the result of processing of all this experimental data. So this temperature is believed to be an absolute zero. Nothing can be cooled down below this temperature because the volume will be already zero or close to zero. Volume cannot become negative. So this is an absolute zero temperature. In Celsius scale, this is minus 273. In Kelvin scale of temperatures, this absolute zero is taken as an absolute zero. And then the temperature of water freezing will be 273 degrees. And then the temperature of water evaporation will be 373 degrees. So such is the Kelvin scale in kelvins. That is, absolute temperature is measured in kelvins when the absolute zero temperature is actually designated as zero. So this is a Kelvin scale of temperatures, and this is a Celsius scale of temperatures. So all these important laws can be easily derived and understood based on this formula which we have obtained. This formula defines the connection between gas pressure, gas volume, and gas temperature if the number of molecules is kept constant. So this is the equation of state of an ideal gas. Equation of state, because the state of an ideal gas is defined by these parameters which enter this formula: pressure, volume, and temperature. Another thing which may be derived from here is also very important. It's called Avogadro Law. Suppose we have one gas at some pressure kept in some container of volume V, and the gas has number of molecules N1, and the temperature is T. And suppose we have another gas kept at the same pressure in another container which has the same volume and probably a different number of molecules, but it's kept at the same temperature. So two different gases are kept in two different containers which have the same volume. And we keep the temperature the same in two different containers, and the pressure will be the same. This is keep the pressure the same. If we keep the pressure the same here, and the volume the same, and temperature the same, then the number of molecules will be the same. So the law says, the Avogadro law says then, that in equal conditions, under equal pressure and equal temperatures, equal volumes of gas contain the same number of molecules. The same number of molecules. You may take 1 liter of hydrogen and 1 liter of oxygen and 1 liter of nitrogen, and if the temperature in all three containers is the same, and the volume is the same, and the pressure is the same, then there will be the same number of molecules. The number of molecules of hydrogen in the first container will be equal to the number of molecules of oxygen in the second container, and that will be the number of molecules of nitrogen in the last container. That is the Avogadro law. Under equal conditions, equal volumes of gas contain equal volumes of two different gases contain the same number of molecules. That's the Avogadro law. So, from this equation of state, we have derived three different laws and Avogadro law, which is the fourth consequence number 4. And now consequence number 5 from the same equation of state. Consequence number 5 is called Dalton's law, or Dalton law. Consequence number 5. Suppose we have a first container which has pressure P1 and number of molecules N1, and we have the second container with different gas and different pressure and different number of molecules, but the same temperature and the same volume. And also we may have other containers with different gases. Each gas will have its own pressure in the first container, in the second, and so on. Pressures may be different. The gas pressure may be different in different containers. But the volume is the same. The volume of the first container equals the volume of the second container equals the volume of the third container, etc. There may be many containers, all of them of the same volume. But there are different gases in different containers, like hydrogen, carbon dioxide, oxygen, nitrogen, etc. Many different gases in different containers. All of them have the same volume but different pressures. For each gas, we can write this equation of state. Let's do it. For container number 1, we have first pressure and volume V equals the first number of molecules Kt. For container number 2, the second pressure differs from the first pressure, but volume is the same, and the number of particles is different, Kt. The temperature is the same. We assume that the temperature is the same and the volume is the same. Only pressures are different and numbers of particles are different. And so on. There may be a number of similar equations. What will happen if all these gases are pumped into the same container? We take the second gas and all this gas is pumped into the first container. And then we take the third gas from the third container and also pump it into the first container. What will happen? The number of particles in the first container will be the sum of all numbers, n1 plus n2 plus etc. The number of particles will increase. The volume will be the same and the temperature the same. So what will happen with the pressure? We must add all these equations and we obtain P1 plus P2 plus etc. times volume equals the total number of particles, which is the sum of all numbers, Kt. So the resulting pressure will be equal to the sum of all pressures, will be equal to the sum of all of the pressures of all the gases. So the pressure of each particular gas is called a partial pressure. It's a partial pressure of particular gas. And what we have discovered using these simple calculations, that the sum of partial pressures will give you the ultimate pressure of the gas mixture. That is the Dalton's law. If there is a gas mixture, so all the gases are kept in the same container, and the volume is the same for all the gases, and the temperature is the same. So what will be the pressure of this gas? The pressure in this gas container will be equal to the sum of partial pressures of each particular gas. Partial pressures of different gases which are compounds of this mixture. So this is the Dalton's law, and it's consequence number 5 from what we obtained from the equation of state of the ideal gas. So this is a very important equation which has many consequences, much more consequences. I mentioned only 5 consequences. Actually, there are many more consequences which we will discuss somewhat later. Now I would like to talk about universal atomic masses of molecules. Atomic masses. The masses of atoms and molecules were measured by chemists who studied different chemical reactions between different substances, including gases, liquids, and solids. And it turned out that a certain amount of one substance, if combined with a certain amount with another substance, sometimes gives you a chemical reaction. Like hydrogen plus oxygen will result, if we arrange for this chemical reaction, we obtain water, H2O. So, looking at the number of atoms, we understand that if there are 2 atoms here, 1 molecule of oxygen consisting of 2 atoms, and here is only 1 atom of oxygen, so there must be 2 molecules of H2O, 2 molecules of water. And so if here are 4 atoms of hydrogen, then here must be 2 molecules of hydrogen. So 2 molecules of hydrogen combined with 1 molecule of oxygen will produce 2 molecules of water. And in chemistry, mostly in the 18th century and also in the 19th century, thousands of experiments were conducted in which different chemical reactions were studied. And what is to study the chemical reaction? It's not only to observe it. What means to study? It means to measure the mass of all the ingredients which are involved in this chemical reaction. So in the experiment, a chemist measures the mass of this gas, hydrogen, and measures separately the mass of oxygen, and then measures the mass of water, which is the result in this chemical reaction. Also, as these are 2 gases, not only the mass will be weighed on the balances, but also when the gas is contained in some container, also the volumes of these gases may be measured. The volumes at the same temperature. And then we can observe this reaction. And apart from mass and volume of the ingredients of the compounds, we can observe how this reaction goes on at different temperatures. And it turned out that 1 gram of hydrogen always reacts with 8 grams of oxygen. 1 gram of hydrogen with 8 grams of oxygen. And in no way this proportion can be changed. 1:4, the mass, the proportion between the masses of the ingredients which are engaged in this reaction. This proportion 1:4 cannot be changed under no condition. You may take 1 gram of hydrogen and not 8 grams of oxygen, but say 10 or 15 or 20 grams of oxygen. You may take any amount of oxygen, but only 10 grams will be engaged in this reaction. Only 10 grams will produce the final water, and the remaining oxygen, no matter how many grams are there remaining, will remain as oxygen. It will never be involved in this reaction. The reaction will absorb only given predefined masses of substances, and the masses will always have a definite proportion, like the mass of hydrogen divided by the mass of oxygen will be always like 1 divided by 8. So starting the chemical reactions, people understood that the masses of substances that react chemically have always proportion like some whole numbers, very close to whole numbers. Whatever substances you take, there are always some whole numbers. And so if we have whole numbers proportion, then it's very convenient to introduce some unit of measurement of the mass of atoms and molecules. So at first the units of measurement may be chosen like this. 1 atom of hydrogen may correspond to 1 unit of measurement, and this unit of measurement is then the molecule of hydrogen will correspond to 2 units of measurement, and atom of oxygen will correspond to 16 units of measurement, and molecule of oxygen will correspond to 32 units of measurement. So in these proportions are derived from different chemical reactions. And this unit of measurement was called universal atomic mass. Sometimes it's denoted by character U. Sometimes it's called Dalton. This unit of measurement is sometimes called Dalton. So the unit of measurement is Dalton, in honor of this physicist and chemist. So there are 2 different notations for this unit of measurement, either U, like unified atomic mass, or Dalton. So the hydrogen atom has a mass of 1 Dalton. A hydrogen molecule has a mass of 2 Daltons. Then it turned out that the actual masses of atoms and molecules slightly differ from this whole number. Slightly differ, either slightly less or slightly larger than this whole number. And so all the masses are not really represented by whole numbers. And all this system turned out to be very approximate. And in order to somehow improve this system of measuring atomic masses, people understood that it's most convenient to accept that the mass of carbon, the most common isotope of carbon should be 12 Daltons, so that the mass of hydrogen atom, would be 1/12th part of the mass of carbon atom. So if originally we take the mass of 1 hydrogen atom as 1 Dalton, then the mistake in calculating all other masses will be larger if we take all masses calculated with respect to the mass of carbon, then the mistake in calculating other masses will be smaller. But this is a minor thing. You may not take it into account. This gives you just a little bit better correspondence between the masses and the whole numbers. So all the masses of atoms are measured in Daltons. And the mass of hydrogen is 1 Dalton, and the mass of oxygen is 16 Dalton, and the mass of nitrogen, for example, is 14 Dalton. And so the mass of nitrogen molecule will be 28 Daltons, etc., etc. You may look at in the table of elements, Mendeleev table of elements, and you will see all the masses there, all the masses of any element. So what is important about it? The important thing is that if we know the mass of one molecule, then we can easily calculate the mass of n molecules. So the mass of n molecules will be the mass of one molecule times n, which is obvious. So if we take different substances so that the amount of substance we take contains one and the same number of molecules, then the masses of what we take will relate just like the masses of atoms. If the number of molecules is the same in some unit of measurement, in some quantity of substance, whatever substance we may take a different substance, and n molecules will have the mass of a different molecule times number of molecules. If the number of molecules is the same, then the relationship between the masses of our substance, the first substance, and the mass of the second substance will be the same as the relationship between the masses of molecules, the first molecule and the second molecule. If the number of molecules is always the same, then this simple formula holds. And so if we take some amount of hydrogen and some amount of oxygen, we know the relationship between the masses of molecules, 2 to 32. In this particular case will be 1 to 16. So if we take the same amount of mass of these substances as the mass of hydrogen and mass of oxygen, which is 16 times larger than the mass of oxygen, if we take large amount of matter, large amount of substance, but oxygen 16 times larger than hydrogen, then we know that the number of molecules there will be the same, because the relationship between the masses of substances which we have chosen will be the same, is the same as the relationship between the masses of molecules. So people understood that in order to have the same number of molecules, we must take a matter proportional to in the amount proportional to the mass of atom. So if we take 1 gram of hydrogen atoms, which is impossible because they will chemically unite into molecules, or if we take 2 grams of hydrogen molecules, H2, or if we take 32 grams of oxygen molecules, or if we take 12 grams of carbon, then all these amounts of matter, this amount of hydrogen, this amount of oxygen, and this amount of carbon, all of them will have the same number of molecules. And this number of molecules, if we take such amounts of matter, is called Avogadro constant. Avogadro constant was measured in many experiments and using many different methods, and it turned out to be about 602 times 10 to the 23 degree. That is the number of molecules contained in 2 grams of hydrogen, or in 32 grams of oxygen, or in 12 grams of carbon, etc., etc. If you know the atomic mass of an element, you know how many grams of this element we take, the same number of grams as its atomic weight is, as its atomic mass is. If we take so many grams of substance, we will obtain how many molecules are contained in 32 grams. This number, which is called the Avogadro constant. It was measured experimentally, and there are many different methods to measure this constant. So if we take, and this amount of substance which contains this number of molecules is called 1 mole. Amount of substance containing this number of molecules, Avogadro constant number of molecules, is a mole. So 1 mole of hydrogen is 2 grams. 1 mole of oxygen is 32 grams. And all these amounts of substance contain the same number of molecules. So if we substitute the Avogadro number here, it means that if we take 1 mole of ideal gas, then we will have Avogadro number, Boltzmann constant times absolute temperature. And this combination of Avogadro number and Boltzmann constant is called universal gas constant, and is actually usually denoted by R. And so for 1 mole of an ideal gas, we have such an equation. Pressure times volume equals gas constant times temperature. This equation, by the way, allows one to measure the gas constant using a simple experiment. We may take some 1 mole of some gas, for example, 1 mole of oxygen. We may take 32 grams of oxygen. 32 grams of oxygen. Put them in a container under the piston. 32 grams of oxygen, 1 mole. Put this gas in a container, in a piston. And we can measure in equilibrium, when we wait for equilibrium, when the temperature is the same all through the volume. In equilibrium, there will be some temperature in this gas, there will be some volume, and there will be some pressure on the gas. We can easily measure pressure, volume, and temperature in an experiment, and then we can calculate the gas constant. It turns out that 1 mole of an ideal gas under normal conditions occupies the volume 22.4 liters. So what is normal condition? Normal conditions is 0 temperature and atmospheric pressure. If we keep the gas at 0 temperature and at atmospheric pressure, then the volume occupied by 1 mole of any gas will be easily measurable volume, 22.4 meters. And then substituting here the volume, the pressure, and the temperature, we can easily calculate the gas constant. So, If we carry out this experiment and then simple calculations, we will obtain that the gas constant will be equal to P, that is the pressure, volume, divided by temperature. And I told you that the easiest way is to choose the pressure as atmospheric pressure and temperature as 0 Celsius. Then the volume will be 22.4 meters, and then we can easily substitute all quantities here and calculate it. It will be something about 8.314. And the units of measurement will be joule over Kelvin meter cube. Joule Kelvin, oh no, it will be Joule Kelvin. It corresponds to 1 mole, so it will be Joule Kelvin by 1 mole. So in many problems you will need this constant, the Avogadro constant and the universal gas constant. And also it's important to mention, while we have a few minutes, that if you have only 1 mole of gas, then the equation of state will be given by this formula. But if there are not 1 mole, but several moles, what will change here? Several moles means that the number of molecules will be larger. So if for 1 mole the number of molecules is Avogadro constant, and for new moles I use the Greek character nu. If we have new moles, like 2 or 3 or 5 moles or whatever, then the number of molecules will be nu times larger. And then, if the number of molecules is nu times larger, then the equation of state will look like this. Pressure times volume equals number of moles, gas constant, absolute temperature. So that is the equation of state when the number of moles differs from unity and when we have several moles, new moles of gas. The number of moles can be calculated as the mass of the gas involved in the container, kept in the container, divided by the mass of 1 mole. What is the mass of 1 mole? For hydrogen it's 2 grams, for oxygen 32 grams, etc. The mass of 1 mole. So, and this is the mass, total mass of the gas, which may be any quantity. So this is obviously the number of moles. And so the gas law can be put in this way. The mass of the gas over the mass of the mole times RT. Sometimes it's convenient to work with a density of gas. Gas density is defined as the mass of the gas divided by its volume. So if we divide this equation by volume, then we obtain here mass divided by volume. That is the density of the gas. And the gas law will look like this. Pressure equals density, gas density, times gas constant, absolute temperature, divided by the mass of 1 mole. So sometimes it's convenient to use the gas equation in this way. So there are many ways to write down the gas law, the ideal gas equation, the equation of ideal gas state. Many different methods, many different ways to put this equation down. If you need to calculate the number of moles, you may use the equation in this way. If you need to calculate the density of the gas, you may use this equation. If you need to work with just 1 mole of gas, you may use this equation, etc. So the same equation may be written in many different ways, depending on which problem you solve. Next time we will solve some problems on this topic, and we will use the gas equation and some other important laws related to this topic. And on this point, let me finish this lecture, and goodbye till next time.